Okay, I really want to go through a whole load of examples of uses of various formulae that we've come across so far, okay, for simple harmonic motion. So, we're going to start off with a mass on a spring, this thing here, whoops, this whole thing is a mass on a spring. The thing at the bottom is the mass, and let's say we're going to displace the mass by 0.1 meters from its equilibrium position, and then let go of it and release it to oscillate down and up and down and up. This is a simple harmonic system, so the amplitude is going to be 0.1 meters, because it starts off 0.1 meters above equilibrium, then it's going to go 0.1 below, and then back up to 0.1 above. Let's just say, for the sake of argument, that the period of the oscillation is 2 seconds. Therefore, the frequency, which is 1 over the period, is 1 over 2, which is 0.5 Hertz. So this is our system. It's a simple harmonic oscillator. It's a mass on a spring, and these are the key parameters. Okay. Now, the first equation, which is on the formula sheet and which we have already looked at deriving, is x equals a cos 2 pi f t, which is valid here. X is the displacement from the equilibrium position, A is the amplitude, F is the frequency, and T is the time. Okay, what this is saying is A is a constant number. Okay, we're assuming these are free oscillations and that they're not going to die away over time. We're assuming there are no resistive forces, so the amplitude of the oscillations remains constant. So A is a constant, but the displacement x obviously changes over time, because this thing is bobbing up and down, so its distance and the direction from the equilibrium position is constantly changing. So x is constantly changing with time, A is a constant, the frequency is a constant, which is a consequence of it being simple harmonic motion. Not all oscillators have a constant frequency independent of other stuff, but this oscillator does. So the frequency for this given setup is constant, and we know what it is, 0.5 Hertz, and the time is obviously going to change. Time is going to move forwards, as it always does. Now, what can we say about this graph to get a feel for it? Well, firstly, it's a cos graph, okay? And a cos graph, an ordinary cos graph, like if this is time and this is x, if it were just x equals cos t or something like that, okay, an ordinary cos graph looks like this and varies between 1 and -1, and it repeats itself every 2 pi radians or 360 degrees. Okay, but this isn't our situation here, okay, because firstly, it doesn't oscillate our thing between 1 and -1. It oscillates between 0.1 and -0.1. And secondly, it doesn't repeat itself every 2 pi seconds. 2 pi being like 2 times 3.14, which is whatever that is, 6.28 seconds or whatever. Okay, ours doesn't repeat every 6.28 seconds. It repeats every 2 seconds, and ours doesn't have an amplitude of 1. So this isn't exactly our graph, okay? That's where all these numbers come in the green equation above. So, an ordinary cos graph varies between 1 and -1, but ours is multiplied by this A, okay? So our graph of displacement versus time is exactly the same shape, the one I just drew. Try and draw it as well as I can. Okay, except starts at amplitude A. Well, I mean, let's even put the numbers in. 0.1 meters, and it goes down to minus 0.1 meters. So this is, excuse me, x in meters. This is time in seconds. Now the whole thing repeats every 2 seconds because the period is 2 seconds. So this would be 2, this would be 4, and then we could divide it up. This must be 1, this must be 3, this must be 5, etc. Okay, so we can already get a feeling for what this cos graph is saying in terms of where the mass is going to be at different times. Okay, so you could get asked questions like, you know, what is the displacement at time t equals, let's say, half a second. Well, when the time is half a second, that is a quarter of an entire cycle. So if we look at this, okay, our entire cycle takes 2 seconds. Okay, 0.5 seconds is a quarter of that. Where's it going to be? Well, x is going to be 0. Okay, what about at a time of 1 second? Well, 1 second is half a cycle. Half a cycle is here, 1 second. Okay, it's going to be at maximum negative displacement, which in this case is minus 0.1 meters, and so on. They could ask you, you know, 1.5 seconds, 2 seconds, whatever. Okay, this is all fine and dandy. It's all easy when it's nice fractions of a cycle that correspond to zeros or maxima or minima. But they could well ask you, what is the displacement x at time t equals 0.2 seconds or something like that. Okay, now you're not going to be able to read that off a sketch graph like I've just done because it's a sketch graph. So what we're going to use is the formula. Okay, we'll say, well, x equals amplitude 0.1 times cos of 2 pi times the frequency 0.5 hertz times the time. Well, they're asking me about 0.2 seconds, so there it is. Okay, and plug that in. Now if you whack that in your calculator, as I will do now, you will get 0.1 times, right, I'm stopping straight away as I'm typing this into my calculator because there's a big pitfall here. This angle here, this is an angle, okay, that you're putting into this expression is in radians. Okay, because we've multiplied all this stuff by 2 pi. Okay, this is in radians. So before I progress any further, I've got to make sure my calculator is in radians. So somewhere on your screen there'll be a little square, probably with either a D in it or an R in it, and you want to make sure you've got a little R in that square. So I'm going to change my calculator into radians so I get the right answer. Okay, sorry for the delay there. Let's crack on. 0.1 times cos 2 times pi times 0.5 times 0.2 close bracket equals 0.08 meters. Rounded slightly, that's not the full answer. Okay. Now if we were to just take a quick look on our little sketch graph, is that plausible? Firstly, this is a positive number, okay, which is a positive displacement. Now if I were to guess where 0.2 would be, okay, I would guess it's about here. Does that look like a displacement of 0.08? Yeah, not bad. Okay, I'm going to trust that. Now let me ask you to do another one. Okay, now let me ask you, what is the displacement at time t equals 2.2 seconds. Can you pause the video, plug that into the formula, and tell me what the displacement is? Do that now. Okay, hopefully you have done it. I am not going to put that into my calculator because I'm hoping that it's going to be the same answer as this. And if it's not, put a comment in the comments and I'll better sort out what's gone wrong. Okay, but this whole graph repeats every 2 seconds, so I'm hoping that at 2.2 seconds, which is about here, the displacement is going to be exactly the same because it repeats every 2 seconds. But it's good practice to put that into your calculator. Make sure your calculator is in the right mode and that you get the right answer. Okay, so this is our first formula, this one here in green now in the middle of the screen again, that you need to be familiar with and you need to be able to put numbers into and put them in the correct units and make sure your calculator is in the correct mode. So that's the first video. I'm going to make a couple more now on the other formulae you need to use.